Okay, so I am audible, right?
Yes, sir.
Yes. So today, right, recording has been started. So today we will start the lecture 20, that is the fourth lecture of graph theory. So I first share my screen. So you can see my screen, right?
Yes, sir.
Okay, great. Hmm. So this is the first lemma. It says that, so let G be a graph in which each vertex has even degree. Okay, that's mean every vertex of that graph has even degree. Now then it says that the lemma says that G has a closed trail starting from any given vertex V. That's mean if you choose any vertex V, if V is you given, okay, then G has always has a closed trail starting from that vertex V. Okay, and also since it is a closed trail and starting from a given vertex V, that's mean that it ends at V as well. Now if you don't remember the definition of trail, I can recall the definition. So it is from the lecture number 1. It was a definition of trail. So trail is just a walk, okay, in which no edge is repeated, but vertices can be repeated. Okay, so this is just a trail. And what is a closed trail? So that's when it is just a closed walk. Okay, that's when it is just a sequence of vertices where the vertices may be repeated, but the edges are not repeated. Okay, so that is called a closed trail. Okay, now we will prove the lemma. So we will prove that it is given that G is the graph where every vertex has even degree, and we will prove that if we choose any vertex V, then we will prove that from that vertex V, you always have a closed trail. So okay, so we will begin with a trail W at V. So we will begin a trail W means it is not a closed trail. That's mean you just start with V and you will just go through any edge. Okay, and since the number of the degree is even, then you can go further, right? I can show you in terms of picture. Suppose this is your graph G. Now you can see that here every vertex has even degree, right? Here it is 2, here it is 4, 4, 2, 4, 4. So that's mean every vertex has even degree. Now choose any vertex, say this vertex. You can choose this vertex as well. So I am choosing this vertex. Okay. And just start from here, go through any edge. Say we go with, say, this one. Okay. It takes a time to uh, what is happening? Why my pen is not working? Just a minute. Uh, I am audible, right? I don't know this computer some
Yes,
hangs.
sir. You are audible.
Okay, now it is working. So we go with this. Okay, so starting V, we go with this one. Now again, now the degree of this vertex is even, and you can see that there are these three vertices. So you can go further. Further means you can go there. For an example, this. Okay. Then again, the number of these vertex, the degree of these vertex is even, so you can go further. So you can go, so you can finish here as well. You can go to this as well. Then you already have a closed trail at V. Okay. Suppose you don't want to go to this number, this vertex. Okay. Then suppose you go to this. Then again, the degree of this is even, say go to this one, say go then this one. Then you have only one choice, right? You have to go to V only, right? So this is, and this. So this is my V and say this is my W. And this red is capital W. Okay, this is the trail. So what we are saying here, so continue this trail as far as possible until a vertex W is reached such that the only edges incident to W already belongs to capital W. Okay, so that's mean we are reaching here. Now again we can go, we have only one edge here, right? Now we can go to this one, right? We can go to this one. This, since this is, see, we can always have a closed trail. Okay, so that's when in this case your this is equal to W. Now the question, now here the theorem, the lemma says, suppose if possible, then we are saying that actually we will claim that W must be equal to V, and here we see that W must be equal to V, right? Now we will prove that actually W must be equal to V for any graph, not only this graph, for any graph. Now suppose W not equal to V. Okay. Now note that each time W encountered on U encountered on W before the last time and for the first time, you can see that one edge is used to enter U and another edge is used to exit from U. Right? For an example, suppose this is your U. You can see that in W we are going to, by this edge we are going to this one, and by this edge we are going out from U. Right? So that's mean in W, if you choose any vertex U, then it must have even degree. Right? And if this is not your W, suppose this is your W, suppose this is your W now, then you can see that the number of degree of V is odd, and the number of W, if it is not equal to V, then it is also odd. And this is also odd for the first time. And for the other vertices, you can see that here, this is, if this is your U, this is also even, this is also even, right? And for the other vertices in W, it is even. But what is given here? What is given here? It is given that see, it is given here. Then see, the W must have an even degree, right? It is given that since every vertex of W is an even degree, therefore W must be an even degree. So therefore, there must be at least one edge incident to W that does not belongs to W. For an example, this, what we get this one. If this is a W and this is odd, odd means you must have one edge from here, right? You must have one edge which does not belongs to W, and this is that edge. If this is your W, then you must have in this edge, and this is a contradiction. Because we assume that the only edge incident with W already belongs to capital W, and therefore V must be equal to W. So this is the proof. So therefore W is a closed trail. So if you are confused with that proof, what we are doing, just it is just a simple one. Since it is given that every vertex has even degree, so we start from one vertex and we go in an arbitrary way. And since again there is even, so you must have one extra edge, and then we go further. and somewhere we will return to V. Because if we cannot return to V, then V and W must have odd degree. Is that clear to all of you? So I can show you in terms of figure again.
So I'm not getting what we are actually doing in the proof. Actually, means I can understand with the figure, but not with the written proof.
Okay, just a minute. So this is your graph. Okay, this is your graph.
Yes,
And
sir.
we choose any arbitrary vertex, any vertex. You can choose this. For an example, we are choosing this one. Okay, now what we need to prove that? We need to prove that you have a closed trail. Okay, you have a closed trail starting and ending at V. So what we will do? We choose V, any arbitrary vertex V, and we start with an edge. For an example, this time we choose this edge, this. Okay, now this is your V. Now suppose this is your W. Now what was the given? The degree of W?
Even
Even. Or how many edges are in here in red color in W?
one.
One. So that's mean you must have another edge of black color,
Yes, sir.
right? But here we have three. So you can choose any arbitrary one. Suppose you choose this one. You choose this one. In my pen is, I don't know what is. So we choose this one. Now this is my W. Okay. And since we encounter here and go out, so this is your U. Now you can see that this U in W has even degree, right? Because we
Mm.
go and out, and this is a boundary. Now again, W has how many? W has we know that the degree of W is even, right? But we have only red colored edges only one. That is a odd number of times, right? So therefore, so we must have another black colored edge. Black colored edge means that edge not in W, capital W. Okay.
Yes, sir.
So we go with further this, for an example, this one. Now again, this degree is even and here we have odd. Then suppose we go to this one again. Now see here again, when you go to this one again, that number of this vertex. Now this is my W. Now number of this vertex, the degree of this vertex is even, right? But we have odd number of red edges. So therefore this cannot be happen. So we must have another black edges from here. And this is this one. To go to this, again go to this, and finally we will reach to V. So whatever direction you go, you must reach to V. That is the main claim. If you cannot reach at V, then you must have another black edge. Black edge means that edge not in that tour, not in that trail, W. Did you get?
Yes, sir.
So that is the
Uh,
proof says actually. Yeah.
in the tutorial sheet 8, there is a question in which we are asked to prove that if the minimum degree of a vertex is greater than or equal to 2, then there exists a cycle of length at least the minimum degree plus 1. So the difference between that and this case is that in this case, we can show that every vertex
No.
where
That is a cycle, right? You are saying that cycle.
so I'm saying that that's something even stricter.
Right, but this is not a cycle.
Yeah. So like if no, so if I prove that it's a cycle, then it's obviously a trail, closed trail,
Right,
right? So I
right.
wanted to ask the difference. Is there any difference between this and that? Like in this case, we can show that every vertex, for this in this graph would have a cycle that ends on it, right?
No. But the problem is here we can repeat the vertices. But
Yeah.
when you call a cycle, you cannot repeat the vertices. So you have to be careful about the cycle and trail. For trail, you can repeat the vertex. For an example, this vertex was repeated
So
here.
like in this proof, if I write that the proof for the case that delta G,
Right. That the proof will be the similar of that one only.
so like if I write that proof, that would be valid in this case also. Is there any condition in which that proof is not valid here? That's what I wanted to ask.
No, that will be fine. That will be fine.
Okay.
But that's when you are saying that you need a closed cycle, right?
Yeah.
Just a cycle, not a trail.
Yeah. But a cycle is a trail.
Right.
A
That is
closed
also
cycle.
fine. That is also fine. That is also
Okay.
fine. Thank you. Yeah. That is also fine. But here we are doing something general. So we can do, since we need a trail, so we can go. We have some extra cases here. But if you want to find a cycle, then we will not have this extra case. That's when it will not back to that one. Okay. Yeah, that is all right. I got your question. So he is saying that instead of finding trail, we can find a cycle. What he is saying, right? So you have said that one only, right?
Yes, sir. Yes, sir. I mean that the proof for that was
Ha.
rather smaller than
Right,
this one.
right,
So
right,
that's
right,
why.
right. Yeah, you can find that one as well.
Sir,
Okay.
one more thing.
Hmm.
Like, can we do something like this that say I start at vertex V, right?
Hmm.
And I know that it has even degree.
Hmm.
So I can claim that it has at least two vertices that are at a length, that are at a distance one,
Right,
right?
right.
Then I go on further and I say that since it's a trail and we can't repeat an edge and each of the vertex has an even degree, then there
Hmm.
must be at least one more vertex,
Right.
right? That would
Uh-huh.
have the distance 2 from V.
Right.
And I go on further and further, and then I claim that since
Graph.
uh, it's a finite
Finite graph.
vertex,
Yeah.
finite
Finite graph.
graph,
Finite graph.
so there must be an edge, a vertex that we've visited more than once,
Hmm.
and whose edge we have included already.
Right. Yeah.
And from there, I can claim that there exists a closed trail.
Right. So
Okay.
there are many proofs. So this is just a even that proof. I have just written this one, but you can easily simplify this proof because what this is nothing. Here what are the main core of this proof is that you just start with this one, go further, and since it is a even degree and number of red edges, that is the number of edges in trail is odd here. So therefore you can go further, and after some stage you must reach at V, because if you don't reach at V, then that number of the final and initial point should be odd.
Okay. Thank you.
So that is the main name of this proof. That is fine. Okay. So this proof is very simple. Fine. Now there is a lemma. So that is the main aim actually of this lemma. So we will use this lemma here. Now it says that let G be a connected graph. Then G is an Eulerian graph if and only if all vertices of G are of even degree. Okay. So G is an Eulerian graph, that G is Eulerian if and only if every vertex, each vertex of G has degree even. Okay. So if you don't know, if you forget that definition of Eulerian graph, again I can recall from here, from lecture 1. So this is the Eulerian graph. So Eulerian graph means a graph is said to be Eulerian if it has an Eulerian circuit. Eulerian circuit means it has a closed trail, okay, which in which you must have every edges of every edges of that graph. Okay, so that's mean a Eulerian trail in G is such that in G that visits every edge of G exactly once, so allowing revisiting vertices. An Eulerian circuit means it is the same as this one, but it starts and ends at the same point. That's all. Okay, so that's mean it is a closed trail. Closed trail means start and end at the same points. Okay, and it must contains all the edges of G and exactly once. That is the meaning of Eulerian circuit. And if a graph has this Eulerian circuit or Eulerian cycle, but it is not a cycle, it may not be a cycle. So better to call it is a Eulerian circuit. Then G is called Eulerian. Okay. So this portion, that is if G is Eulerian, then all vertices of G has even degree. That part is very simple. Why? If G is an Eulerian graph, so it contains an Eulerian circuit W. Okay. Now again, since W is a just a closed trail, okay, and it contains every vertex of G, then you can see that every times when you take a vertex, say V in W, right? Then each time an edge of W go to first go into V and then exit from V. So that's mean whenever W meets V, okay, then it add exactly degree 2. And it depends on that how many times W meets V. If it meets exactly once, then degree of V will be 2. If it meets exactly 2, then the degree of V will be 4. If meets exactly 3 thrice, then the degree of V will be 6, like that only. Okay. So if you have a closed circuit, Eulerian circuit W, then you have to just find that how many times W meets a vertex V. And depending on that, you can find the degree of V, and it is always even. Is that fine? We have already explained this one in the lecture 1, I think.
Yes, sir. Yes, clear.
Right? That is clear. Now, what about the reverse one? That's mean if a vertex has even degree, if if all the vertices of G uh, have even degree, then G must be a Eulerian graph. Now that portion we will use the induction. Okay. So first of all, what we will do? So let G be a connected graph in which every vertex is of even degree. Now, since every vertex of G is of even degree, by the previous lemma, G has a closed trail starting and ending at a given point V, or you can find a cycle as well, starting and ending at the same vertex V, right? Now let W be that trail. Now if EW equal to EG, then we are done, right? Now if possible, EW is strictly less than EG. Then what we will do? Then we just delete all the edges of W and we consider a new subgraph Z. Now note that degree of so in G every vertex has even degree. In W every vertex has even degree. So if you remove that all the edges from W, all the edges of W, then all the vertices in Z, that is also even. Right? Now since G is connected and W touches, so therefore W touches Z at least one vertex, say W J U. Right? Now again we use the previous lemma. So we can what we can get? We can get a closed trail starting and ending at W at U. Okay? In Z. And then that closed trail in Z combined with W, it will be a new closed trail and starting and ending at V. And if you do this process again and again, After some step, you will get a closed trail which contains each edge of V, and therefore G is Eulerian. Okay, so if it is not clear, we will do this here again in terms of figure. Now we can take again this figure again. So here each vertex has even degree, right? So therefore this graph should be Eulerian. Now we will prove that why this is Eulerian. Now what we will do? We first choose this vertex V. Okay. Now we can find a first closed trail. We know there is a closed trail. So we will find a closed trail first. Okay. So this is your closed trail. And someone said that okay, you can find a closed cycle. So we can find that one. The simple one. So this, this, and this. Okay. Now what we'll do? So this is we just delete this one. So this is V. Okay, we can just the name. Okay. So this is V. So V1. So V2. So V3. So V4. So V5. V6. So we have already W equal to V1, V2, V3, V4. Okay, so this is my first trail, first closed trail for V1. Okay, now what we'll do? We delete this W from this graph. Okay, delete this W and we find a new graph that is Z. Z means just black colored one. Okay, so are you following what I'm saying? First we draw one closed trail. It is possible by the previous lemma. And now what we will do? We will delete these edges. That's mean we will delete the red edges. Now look at the only black edges. So that is your Z. So now Z means black edges graph. Okay. Now since the graph G is connected, now this W1 and Z intersect at a vertex. Now can you tell me at what vertices, what are the vertices where W1 and Z intersects? Yeah, can you tell me that? Yes.
Sir, all vertices V1, V2, V3, and V4, these four vertices.
These four vertices, they are intersecting. So choose any one. So
Yes,
you
sir.
tell me. You can choose any one. So choose one. Tell me which vertex you want to choose now.
V1.
V1 you want to choose V1. Okay. Now look at the black vertices and you choose V1. So this is you choose. Now again. Now look at the black vertices. Now again you have a closed trail. So go with this. Now this is since what? So you have only one edge to go further. So this. Now you have only one edge to go further. So this, this, this. So you have one W2 that is V1, V5, V2, V4, V6, V3, V1. Right? So this is a cycle as well as this is a tour. So we get this one. So therefore your W is now combination of this. So V1, V2, V3, V4, V1, V5, V2, V4, V6, V3, V1. So this is your new W. Now this is your closed Eulerian trail. So our Eulerian circuit in this G. You can now verify it is a Eulerian cycle. So first V1, V2, V3, V4, V1, then V5, V2, V4, V6, V3, V1. So this is your Eulerian circuit. So that's mean it is a closed trail where it contains each edge of G exactly once. So therefore this graph is Eulerian. Is the proof clear?
Sir, basically why we are using the induction is like we can make the argument like there are exist different trails starting from B1 and which there means there is a different closed trail starting from B1, so we can take one trail and then remove the edges involved in that trail, and again then we can take another trail and then remove those.
We are doing that one only, right? You cannot choose every time V1. It might happen. It may happen that if you have only one trail from V1. Now if you remove that one, then there will be no vertex V1 there. It might happen there, right? Did you get what I am saying? So it may happen that you have here you are getting exactly two what should I say, two trail from V1, but it might happen that, for an example, if you choose your starting what is V5, then you have exactly one trail, not true. And we are doing this one only, right? What you are saying, we first choose one trail and we remove that trail, and for the remaining graph you are getting another trail, and since the graph is connected, so we can combine those trail. And similarly, if they are not taking all the vertices, all the edges of G, then we remove both, and then again we do this. And since the graph is finite, so after finite number of steps, we will reach to some stage that one Eulerian cycle, Eulerian circuit will contain all the edges. Yes? No?
Yes, sir.
We are doing that only. What you are saying, we are doing that only. So we are removing one circuit, and then for the remaining graph, we are applying again the previous lemma.
So, sir, how will we prove that there exists a vertex that which will be involved in all the trails? Yeah, like we give, like if we choose B5, then we won't be able to find
No,
the.
I did not say that. One student choose V1. I did not choose V1, right?
So, sir,
But
if first we choose B5,
you can choose V5. Then you can okay. I can do this again. So first of all, right? Okay. Now you understand this one. Now again for this. Okay. So first W1 is say V1, V2, V3, V4, V1. Right? Now you remove this part. Now whenever you have Z means black colored vertices, right? That is here green colored. Then you can choose V5. Now your Z will be this one starting from V1, V5. So V5, V2, V4, V6, V3. Oh, sorry, not V5. So you need to choose one vertex which is common. So here V1 is common, V2 is common, V3 is common, V4 is common. All the four vertices are common here. So you have to choose one of them. Say V2. Then your W2 will be V2, V4, V6, V3, V1, V5, V2. Right? Now you can combine W in this way. So V1, V2, and then V4, V6, V3, V1, V5, V2, then V3, V4, V1.
so the next time if we choose a vertex, then we have to choose this vertex from this W, right? It means suppose we have more trails in this. It means
Right.
more
So
trails.
you have to choose a common vertex of which is common in first W1 and Z. Since the graph is connected, so there must be one vertex common. Right? If there is no common vertex, then there will be disconnected graph, right? You are not getting what I'm saying?
Sir, this proof I'm trying to get it means I'm not able to get this proof.
No.
They are
If you have
connected.
W1 and if you have Z, if there is no vertex common, so that's when the graph will be disconnected, right? Because
Yes,
how we are getting Z? We are removing all the edges of W1 and we are getting Z.
yes, sir.
So that's mean the edges of W1 and edges of Z, they are not common, right? Now if there is no vertex common, then the graph will be disconnected.
Yes,
But
yes.
since this is a connected graph, so there should be a vertex common of W1 and Z. And choose any of these common vertex and you find a trail from this one. For an example here, V2 is common and you can choose that V2 and you can find that trail from V2, starting and ending at V2. And just put this one here. In place of this, you just put this. Okay,
Yes, sir.
right. Just go through the proof and take one example. You take one example and go do this. Then you will get the proof. Now this is the easiest way to get a proof. The proof is very easy. Okay. Now I think I have defined this one. If not, again I can define this one. What is the delta G? So for a graph, delta G denotes the minimum degree of the vertices. So this is the delta G. It is the take the degree of vertices and take the minimum of that. For an example, if you take this graph, then delta G will be 2 because degree of V5 is 2 and degree of V2 is 4. The minimum degree is 2. Okay. And what is Hamiltonian graph? We have already defined this in the lecture 1. So let G be a graph. Now a Hamiltonian path in G is a path that visits every vertex of G exactly once. Now there is the main difference of that Eulerian graph and Hamiltonian graph is for the Eulerian graph we need a trail which visit every edges of G exactly once. And for the Hamiltonian graph, we need a path. We need a path which visits every vertices exactly once. Okay. And a Hamiltonian cycle is again it is a cycle in G that visits every vertex of G exactly once. Now, if such a cycle exists in G, then the graph G is called Hamiltonian. Now you maybe ask this kind of question. Suppose this graph is given. Okay. Now you might be asked that is this graph Hamiltonian? Now if there is a theorem to find that Hamiltonian, then you can use the theorem and you can say that okay, this is Hamiltonian because it satisfies these properties. And if doesn't satisfy any known theorem, then there is another approach is just try to construct a Hamiltonian path, Hamiltonian cycle, and then you can say that this is Hamiltonian. And here you can try to find a Hamiltonian cycle. And here we got one Hamiltonian cycle. See this one. So this is a cycle which contains every vertex of V, every vertex of G exactly once. So this red colored cycle is a Hamiltonian cycle. So therefore the graph is Hamiltonian. Okay, so this is one Hamiltonian graph. You can find another Hamiltonian graph. Now there is a homework. So you just start with this graph and you try to find another Hamiltonian graph other than this red colored cycle. So it is easy to find actually. So this is not unique. You can easily find another Hamiltonian cycle. Now there is a theorem by Dirac. He says that if H is a graph with n number of vertices, where n is bigger or equal to 3, and if degree of V is bigger or equal to n by 2, for each vertex H, then H is Hamiltonian. Okay. So as a consequence of this, you can also prove that that Kn is Hamiltonian, right? Also, it is easy to find it is Hamiltonian because you can draw any graph, any cycle there, because all the edges are connected. So anyway, so now if you have a graph, for an example, this theorem you cannot apply here, right? Because here number of vertices, what is the number of vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like that. But uh, the degree of each vertex is exactly 3. So therefore, this you cannot apply this theorem here. So therefore, you need to do by hand only. So to show that this type of graph is Hamiltonian, you need to find the graph. You need to find the Hamiltonian cycle. So this is the procedure only. But if you are given to a graph where degree of V is bigger equal to n by 2 for each vertex H, V in H, then you can say that H is Hamiltonian. And here is the proof. Now again we prove via contradiction. So now we prove that we assume that if possible, let there be a non-Hamiltonian graph H in which degree of V is bigger equal to n by 2. But yeah, but the H is not Hamiltonian. That's mean you first assume that there is a graph H where degree of V is bigger equal to n by 2, but the H is not Hamiltonian. We assume this one and we will get a contradiction. Okay. Now what we will do, starting with such H, okay, and now try to add some edges and we get G be a maximal non-Hamiltonian graph on the same vertex set containing H. Okay. So that's mean we are just adding the some edges and we are getting G in such a way that obviously since G has more edges and the vertex set is same, so therefore degree of V is bigger or equal to n by 2. And what do you mean by maximal? So that's mean if we add any extra edge in G, then the resulting graph will be Hamiltonian. And such graph exists, always exist. Why? Because you can choose, say for an example, Kn, okay, and then H subset of Kn, and Kn is non-Hamiltonian. Kn is Hamiltonian, right? So therefore, H subset of Kn and Kn is Hamiltonian, H is non-Hamiltonian. Now you can try to find a graph G which lies between H and Kn and which is not Hamiltonian, but this is the maximal non-Hamiltonian. That means if you add any extra H, then that will be Hamiltonian. So is that clear? What is your G? Yes.
Yes, sir.
Okay, fine. Now since is maximal non-Hamiltonian, oh sorry, okay. Now again, now G cannot be equal to Kn. Why? Because Kn is Hamiltonian, but G is not Hamiltonian. So G is not equal to Kn. So therefore, there must be one, no, there must be two vertices U and V in G such that UV is not in G. Right? Because G may not have all possible edges. Otherwise, G will be equal to Kn. So therefore, you must have one edge in Kn which is not in G. Now, since G is maximal non-Hamiltonian graph, so therefore G plus UV is Hamiltonian because we are adding one edge UV, then it must be Hamiltonian, right? Because G is the maximal non-Hamiltonian graph, so we cannot increase more edges from G. Okay. Now since G plus UV is Hamiltonian, so let C be a Hamiltonian cycle in this. Now that UV should be an edge in C. Why? So if UV is not an edge in C, then C will be a Hamiltonian cycle in G as well, which is a contradiction. So therefore UV must be an edge in C. So therefore C will be look like this one. So this is just n cycle, right? So it's starting with U, which is your V1, V2 up to Vn, which is V, and then U. This is your cycle. Now this is a trick. So how to define your S and T? So this is a trick. You have to remember that trick. Because of that trick, this proof is famous, and therefore the name is the Dirac theorem. Because he find that trick. Okay. So what is that trick? So construct two vertex set S and T in this way. So what is S? S means we take all the Vi from C, or you can say all the Vi from the graph G, because C and V have same number of edges, same number of vertices, and that is V1, V2 up to Vn. Okay. So S is the So S is the collection of all of the vertices of G. You can say G or C, same, such that V1 and Vi plus 1 is an edge in G. Remember that. We are choosing Vi so that Vi plus 1 is an edge in G. And what is the collection of T? Now T is the all the collection of Vi in G such that Vn is an edge in G. Okay. So did you get what is S and what is T? Note that for T we are taking all the vertices adjacent to Vn. We are taking this. That is T. T means all the vertices adjacent to Vn. Okay. And what is S? We are taking first all the vertices adjacent to V1 and then taking the next vertex of that. And that is, sorry, previous vertex of that. That is your collection of S. So is that clear? What is S and what is T? So T means the collection of all the vertices which is adjacent to Vn, and S is the collection of all the previous vertices. We first take the collection of vertices which are adjacent to V1, and then we take the previous vertex of that, and that is called S. Okay. Now from this, can you say that Vn does not belongs to S? Now tell me why Vn does not belongs to S? Yes, I am waiting for your answer. Why Vn does not belongs to S? Yes, I am waiting for your answer. You are not listening?
So Vn plus 1 would be U, right?
Right.
So V1 is U and
V1
there
is
is
U.
no self loop.
Right. So therefore Vn not in S. Good. And why this is not in, why Vn is not in T? Again for the same reason. Right?
Yes, sir.
So therefore Vn not in U, so not in S, and Vn not in T. So therefore Vn is not in S union T. Right? Now what will be the union of this one? That is what is the then what is the cardinality of S union T? It is less than N.
Yes, sir.
Right? Because Vn is not in
Vn
the
is not there.
this
Yes.
set. So therefore their cardinality is less than N. Fine. Now we claim that their intersection is also empty. Now we claim that their intersection is also empty. Why? Now if suppose Vk, okay, now we can show in terms of figure. C. This is your C. So V1, V2, V3, V4 up to Vk this one. Right? Okay. Now suppose that intersection is non-empty. Say Vk belongs to S intersection T. What do you mean by Vk belongs to S intersection T? So that's mean V1 Vk plus 1 is an edge in G and Vk Vn is an edge in G. That's the meaning by Vk is belongs to S intersection T. Right? So therefore V1 Vk plus 1 is an edge and Vn and Vk is an edge. Okay, so first you have a Hamiltonian cycle C1, say it was sorry C, that is Cn, V1 which is your U, V2, V3 up to Vn. Vn means V and V1, that is U. So UV was in C. So this was your Hamiltonian cycle in C, sorry, in G union G plus UV. This was the Hamiltonian cycle. Now, if there is a Vk in S intersection T, that's mean if there is these two edges are there, then you can get a Hamiltonian cycle. So you can get a new Hamiltonian cycle C dash, Cn. You can start with V1, okay, then V2, V3, V4 up to Vk, okay, and then you go to the Vn, then go to the Vn, then Vn minus 1, Vn minus 2 and up to go to the Vk plus 1. So you start with this in this direction, then go this direction, then go to this direction and then this. Oops. Okay, I just missed one part. What is that? Okay. Go to this direction, this, and then go back to this one, this. So Vn, then V1 to V2 up to Vk, then Vn, then go to Vk plus 1 and then V1. Now take this cycle. Now this is a Hamiltonian cycle because it contains each of the vertices V1, V2 up to Vn, right? Now can you tell me this vertex, does this vertex contain UV? The edge
No.
UV?
No.
No, right? So that's mean it is a Hamiltonian cycle G plus UV as well as it will be Hamiltonian cycle in G as well.
Yes.
But that is a contradiction because we have assumed that G is the maximal non-Hamiltonian cycle, a non-Hamiltonian graph. So therefore this graph is a Hamiltonian cycle in G, that is a contradiction. Okay, so therefore you can say that this is empty. S intersection T is empty. Now since they are empty, so therefore du plus dv, that is degree, that is this plus this, and since their intersection is empty, so there's this sum is equal to this sum, and we have already proved that this is less than n because Vn is not there, so this is less than n. But it is given that V1, degree of V1 is bigger or equal to n by 2, degree of Vn is bigger or equal to n by 2, so therefore their sum is bigger or equal to n, and this is a contradiction. So we prove that, we assume that H is not Hamiltonian and we find a maximal non-Hamiltonian graph G and we get a contradiction. So therefore H must be Hamiltonian. So we are done. So this is the proof. So how to prove this one? So if any graph satisfies this condition, then it is Hamiltonian. So we first choose a graph. So we will prove by the contradiction. So we assume that there is a graph H which satisfies this condition but not Hamiltonian. Then we choose one G which is containing H and it is the maximal non-Hamiltonian graph. Then G lies between H and Kn. And then we get a contradiction. So therefore H must be Hamiltonian. So we are done. Okay. So go through that proof. I am sure that you will get the proof. Now in the similar way, so there is another theorem by Ore. So that is the similar proof. Now it says that the theorem says that let G be a graph with n vertices and let U and V be non-adjacent vertices of G such that degree of U plus degree of V bigger or equal to n. Okay. Now they prove that G is Hamiltonian if and only if G plus UV is Hamiltonian. Okay, now here is the proof. The one portion is very simple. If G is Hamiltonian, then G plus UV must be Hamiltonian because it is a super graph and there is no extra vertices. So therefore this portion is very simple. So if G is Hamiltonian, then G plus UV is Hamiltonian. So there is nothing to prove here. This is trivial. Now we will prove the reverse part. So we assume that G plus UV is Hamiltonian. We assume this. And now we prove that G is Hamiltonian. So let C be a Hamiltonian cycle in this. Now if UV is not in edge in C, then C will be Hamiltonian cycle in G. So we are done. There is nothing to prove. So the only case remaining that G plus UV is Hamiltonian, C is a Hamiltonian cycle and C contains the edge UV. So therefore the Hamiltonian cycle will be in this way. So this will be a n cycle. So V1, V2 up to Vn, where V1 equal to U and Vn equal to V. Now similar way we can define S and T. S means we first take all the vertices which is adjacent to U and then we take the previous edge, previous vertex of that cycle. This one. And what is T? We just take that adjacent vertices of V. Now by the similar argument, you can see that since G does not have any loop, so V is not in S because right, because V, what is V? V means Vn, right? So if Vn in C, Vn in S, that's mean U Vn plus 1. Vn plus 1 means U only. So U will be an edge. That is not possible. And similarly, VB is not an edge. So therefore Vn will not be here. That is V not in there. So therefore V is not in here. Therefore V is not in T union S. Okay. Now since C contains all the vertices in G, so therefore cardinality of S will be degree of U, cardinality of T will be degree of V, and their union, the cardinality is less than N because V not in this. It should be strictly less than N. It cannot be N because Vn is not there. Now if their intersection is empty, then du plus dv will be this one equal to, which is equal to this sum because their intersection is empty and that is strictly less than n. And this is a contradiction because it is given that this sum equal to n, bigger equal to n. So this is a contradiction. So therefore this should be non-empty. Now let there be a vk in S intersection T such that intersection T, and that's mean V1 Vk plus 1 and Vn Vk are edge in E, and then we get this Hamiltonian cycle in G in the same proof. So therefore G is Hamiltonian. So this is the similar proof actually of the previous proof, Dirac, proof by Dirac. Okay, so we are done. So any questions of this theorem and this theorem? Dirac and Ore? So let me know if you have any doubt or if you have any question or if you have any other query. Yes? Okay, fine. Now this is the another concept, that distance of a graph. So let G be a graph. Now you can define a metric actually. So okay, we have to prove this is a metric, but we can define a function from V cross V to N defined by dxy means the shortest path between x and y. Shortest path means the length of shortest path means the number of edges between x and y. Okay, the shortest one. For an example, if this is u and this is v, then dxy is 1 because there is only one edge. Now if this is u and say this is v, then the distance will be 2. So 1, 1, 2. So in this way we define the distance. And if there is no edges between x and y, okay, that's mean if in case of disconnected graph, then we just define dxy equal to infinite. But if you have a connected graph, then dxy should be a finite number, right? And obviously if x equal to y, then this is 0. Now the exercise is, if G is a connected graph, then you have to prove that this is a metric. So you know the definition of metric, just verify that this is a metric, because we will use this metric later, or maybe in some tutorial problems. Fine. So this is all for today. So again, I ask you, so if you have any doubt, if you have any question, you should ask. Or if you don't have question, you just go through the lecture notes. And if you have any question, you can ask in our MS Team group. Okay.
Thank you, sir.
Sir,
Okay.
I have a doubt.
Yes.
Sir, I have sent an image in chats.
So this is a vertex or not?
I guess no, sir.
Okay. Yeah, so every vertex has degree even, right?
Sir, I'm not sure about that loop part.
This one.
No, sir. Yes, sir, that one.
No, that is fine. Nah? It's 1, 2, 3, 4. Here is 1, 2, 3, 4. Even if you consider this vertex, this is also 1, 2, 3, 4. Even it is not by vertex, then also it is fine. This is also 1, 2, 3, 4. This is 1, 2, 3, 4.
So, sir, can we draw this without lifting pen and repeating edges?
Not repeating edges, right?
Yes, sir.
Yeah, you can do that.
Sir, but we have tried in childhood days, but we could not do that time.
It is given, right? So a connected graph is Eulerian graph if and only if all the vertices are of even degree.
Sir, so we can draw this.
Yeah, you can draw this.
Okay. Sir.
So what you can do first,
Rameshwar,
you can follow that for one. Yeah.
So we can take let's say we take the top point of the left edge of the square, right? We go down.
Yeah. First, what
diagonal.
I'm doing, so you can just follow the proof first of all. What you can do, you first delete that one. Okay, you can start go to this. Okay, so this 4 complete. So you see 1, 2, 3, 4. Okay, now the 1, 2, 3, 4. We are done.
Okay, sir.
Get? See,
So, but I thought he said you can't repeat vertices. This won't be possible, right?
vertices or edges? No, you said edges.
Okay,
Vertices or edges?
I thought he said both. Like you can't lift your hand. That means you can't repeat.
No, it is given that right without lifting up and repeating edges. Edges, he said, not the vertices.
Okay, sir. Got it.
So 1, 2, 3, 4, and then 1, 2, 3, 4. So you are done. Since all the vertices have even degree, it should be Eulerian graph. So therefore, you can easily draw that.
Okay, sir.
And when you said not repeating the vertices and edges, then you need that Hamiltonian one.
Yes, sir.
But for this one, we do not know any proof, any theorem for the Hamiltonian. We know only that one. If degree is bigger equal to, that is also fine. I think you can do that one as well. Because what is the number of vertices? 1, 2, 3, 4. Right? Even you can take 5. And right. And what is the degree? Degree of every vertex is also 4. So therefore, that is also possible.
So, but in that we'll violate his condition for not lifting your hand. Like you can't do that here, right? Because it's not exactly what he's asking.
No, you can just do this one. That take this cycle 1, 2, 3, 4. You are going through all the vertices. And if you are saying that all the vertices and all the edges and not lifting, not repeating the vertices, so that is a funny question, right? That is not possible because if the degree is more than 2, you have to repeat the vertices.
Right, sir. Got it.
Right. Yeah, that is a good question. But yeah, this kind of question may be in during exam. Okay. Now do practice all of this type of question. For an example, we can give one graph and we have to we may ask you to find a Eulerian path or Eulerian circuit, or you can say that yeah, the graph is Eulerian or not, and to find a Eulerian circuit, and we may ask that find a Hamiltonian cycle. Okay, and if you have a graph where there are some odd degree vertices, then you can easily say that it is not Eulerian because it is a if and only if condition, right? It is Eulerian if and only if all the vertices should have even degree. Because do you remember in the first day, I think we had one theorem, one bridge problem, right?
Yes, sir. Königsberg bridge problem.
Yeah, the first one, right? So that was not possible because degree of this vertex, even in fact, every vertex is odd, not even. So it does not have even a odd Eulerian circuit, not even Eulerian path as well. Okay, so this type of problems are very interesting. So I wish you should try this kind of problem. Now you have some good books as well. Just try from there as well. Okay, and also you solve the problem from the tutorial sheet. And also try from the, yeah. So there are some, I have referred a book, right? By Distill. So you can try some problem from that book as well. Okay, so see you then in the next lecture. Okay, we can end the meeting.
Thank you, sir.
Okay.
Thank you.
Thank you.